Hi there, my name is Christopher Collison, and we're going to continue through the third lecture in this series. That's the course CHMP 442. And what we're going to try to do here in this particular section is I'm going to throw out some bits and pieces that are going to be important for you to take on as we move forward in the course. These I'm calling steps in the right direction. So where we left off, we're recognizing that there are these three observations that are driving forward the need for quantum mechanics. So in this particular segment, we're going to talk about Niels Bohr and his assumptions for quantizing angular momentum, which we'll find out is something that's very important as we get to weeks 7 and 8 in the course. We're also going to talk about de Broglie, and de Broglie is basically saying, well, you know, if Einstein can have his particles that are important for the photoelectric effect, then why can't I have my electrons be waves? So Einstein's light was photons, was particles. So de Broglie is saying, can we not have matter waves? And that's actually going to lead us towards Schrodinger's introduction. And Schrodinger should have a note on the there. So Schrodinger. This is going to bring Schrodinger's involvement into quantum mechanics because he's a waves guy. So we'll see where he comes into play in future lectures. We're also going to introduce something called the Bohr Radius, and we're also going to tie some loose ends up associated with the atomic spectra and the Rydberg Constant that came up in the last lecture. So let's jump straight in. These things may seem a little disjointed. The idea is that they will connect together a little more as we move through the course. So we're actually going to start by thinking about Rutherford's model. So in Rutherford's model, we have our nucleus here, and we have an electron that's imagined to be circulating around that nucleus like planets do around the sun. The paradox here is that in principle that electron would eventually come spiraling in and would annihilate. The electron would give off energy as it ultimately comes crashing down into the nucleus, and that doesn't happen. And so, the more we understand about our universe, the more crazy it sometimes seems. The more we think we understand it, the more we then realize we need more things in order to know what's really going on. So that's the problem with the Rutherford's model, but we're going to use it a little bit to derive a few ideas, quantization of angular momentum and the Bohr radius. So what we'll do is we'll start with Niels Bohr in 1913, and he's actually proposing that spectral lines come from these transitions between different energy states within an atom, and that the electron moves from one state to another. So from a state to E sub 1, for example, to a state E sub 2. And with this in mind, he made some assumptions. And so he's saying, well, yes, if there's light that's coming in, and that light has an energy of E nu, and really what that energy is the gap between these two states, E2 and E1, then we can recognize this in this equation in here. So he's also saying, and these are the assumptions that he's making. So these are very new ideas. They don't they help us along. They move us along. So Niels Bohr is also saying that in these discrete states, so E1 and E2 are these discrete states, the magnitude of the angular momentum of the electron can only have values determined by this integer, right? So he's putting forward this fact, this idea, this assumption. So the angular momentum L in here, he's saying, is equal to n multiplied by h over 2 pi. One thing I want to have you recognize is that we're going to come across this a lot. This h over 2 pi term in here, we're going to call this h bar. We're going to see that a lot in our course. Okay, so the other thing again here is that he's saying this n is an integer. He's also saying that the behavior of an electron can't be visualized or explained classically. So that's right off the table. So a little disjointed. Let's see whether it comes in as we drill down a little deeper. So we're actually going to come back to this idea. So we're going to go off on a side and say, well, let's think about Einstein and de Broglie. And the reason I mention Einstein is because around the turn of the century, around the 1900s, Einstein is developing his special theory of relativity. And this is where the idea of E equals mc squared comes from. And in this particular equation, which is given fully here for completion, m is the rest mass, and p is the momentum of the photon in this case, and c is the speed of light, the velocity of light. For radiation, so when we're talking about radiation, the relativistic rest mass of a photon is actually 0. So this term in here is going to go to 0 because the rest mass of the photon is in fact 0. And that's going to lead us to, when we take the square root of this term up here, it's going to lead us to the equation provided at the bottom of the page. So the photon is considered to have this momentum, and E is equal to this momentum multiplied by C. So C, of course, also using our waves equation, the speed is equal to the wavelength multiplied by the frequency, and that's provided here. And so we end up with an important expression at the bottom. So when we move on to this next line, so what we're finding here, of course, is also from Planck, right? So we've recognized in the quantization of photons, E is equal to h nu, okay? And which we're also saying from de Broglie's work is equal to the momentum times wavelength times the frequency. So basically now what happens is we can cancel through these frequencies and we're left with lambda is equal to h divided by p. The p comes down, and here's an equation that is really something that we're going to consider to be for a matter wave. So at the moment, this expression that I'm talking about up here is for the photon, okay? But so this is for the photon, but de Broglie is suggesting that kind of all matter and light may be sort of similar in some way. He's saying, hey, if Einstein can have particles for his light, then let's have waves for our electrons. So he's basically saying this parallel expression would apply to a beam of particles of momentum p and velocity u, okay? And m is the mass of the particle. So he's splitting up the momentum here into mass times velocity. So let's have a look at an example. And the example here is an electron. And we know the mass of an electron here in system international units of kilograms, and 9 times 10 to the negative 31 kilograms. Here's the fundamental charge. And we're going to accelerate this electron towards a positive charge. We're going to accelerate it through a potential of 100 volts. So again, using classical physics, we can recognize that energy is equal to the charge multiplied by the voltage difference here. So fundamental charge multiplied by that voltage gives us an energy in joules. We're using system international units throughout. And so we end up with 1.6 times 10 to the negative 17 joules. We also, of course, recognize, kinetic energy is equal to, we're going to come across this a lot, half mv squared. In this case, the velocity is given as u. So that's classical mechanics. Kinetic energy half mu squared here, and that's being equated now to the energy of these electrons that after they've been accelerated. So we can solve for u in here, and we end up with a value of about 6 times 10 to the 6 meters per second for the velocity of those electrons. So now we are actually going to calculate what we call the de Broglie wavelength in here. So we plug in these numbers, we know what Planck's constant is, Okay, we can go look that up. We've got the mass of our electron, which is provided at the top of the page, and we've got the velocity that we've already calculated in here. And from that, after we've done the math, what we find is we have a wavelength here that's 123 picometers, or 0.123 nanometers, or about an angstrom. And if we think about crystals and atomic spacings, an angstrom is usually similar to a bond length as well, right? So it's the spacing between atoms that we'd find in a crystal. So when the spacing is on the same order of magnitude as the wavelength, we know from waves theory that we're going to get diffraction. And so the question that this theory asks, that de Broglie's theory asks, is really, can electrons be diffracted? If they do indeed have wave-like properties, and it turns out they can be diffracted, and this was proved later on, and there's a little story in your textbook that talks about this, but that prediction was confirmed experimentally. So yes, indeed, matter does have a wave property to it. And this is very important because what, as chemists, we want to think about all the time is electrons, and it turns out that electrons have this wave-like property too. So, as I've just mentioned, electrons have these wave-like properties, and so now we're going to connect the de Broglie matter wave approach. We're going to connect that to this interpretation of Bohr's hypothesis, and that angular momentum is quantized. So we're going to think about the orbit of an electron, and we're going to think about if that electron was wave-like, and it must stay in that orbit around the nucleus. If it's to stay alive, if you will, as a wave, then basically we can't have destructive interference as that wave comes around the orbit and kind of interferes with itself. So there's a requirement, in fact, that for a circular orbit, we must have a certain integer number of wavelengths that fit within the circumference of that orbit. So this is all stated on this particular slide. So the circumference of the orbit, by the way, circumference is equal to 2 pi r. And so I'm saying here, if we think of the wave fitting into our circumference, it's got to be a standing wave. So we'll know what a standing wave is from physics. The quantization comes naturally with n. And we're going to find later that Schrödinger got involved with this because, again, he's recognizing that all these integers come from naturally from wave equations. So he's seeing the importance of wave equations that are required to help us to describe what's going on with these electrons. So I'm just pointing out in these last two bullets that, you know, if we don't have this constructive interference, the orbit wouldn't be allowed. It would kind of collapse. So the key here is that with this integer, you know, because we know that the electron has to have a certain constructive interference of these matter waves within the circumference of the orbit, this in itself leads to a quantization condition. So here's our circumference. We know that for a standing wave, there can only be an integer number of wavelengths that fit within that circumference. And so we rearrange this expression. And of course, we also know what our de Broglie matter wave is. So that lambda is equal to h over the momentum, which is h over mu. So this expression now turns into nh over mu. So we're substituting in for the matter wave by de Broglie in here. Okay, so we end up with an expression, the mass times the velocity times the radius, so that's that angular momentum, is equal to n times h bar. So that's what Bohr had postulated. And so there's some consistency here with de Broglie's relationship leading to this quantization condition. So this is where I'm saying with these bits and pieces, there seems to be some kind of thread of progress. It's leading us towards recognizing that we have to have some kind of mathematics associated with waves if we really want to try to address the confusion that came about from line spectra and so on. What we're going to turn our attention to now is the Bohr radius, and so we're going to think a little bit more about these orbits, and we're actually going to borrow some classical physics. So we're going to recognize Newton's second law. Okay, force is equal to mass times acceleration. We're also going to recognize Coulomb's law, and that the force of attraction here, if it's negative in here, by the way, is a force of attraction. And so we've got a positive charge on the nucleus. So Z is the nuclear charge and E is the fundamental charge. The E that we have here, of course, is the fundamental charge on the electron. That's negative, and so that negative will transfer towards when it's negative, this is an attractive force. We've got the distance between the electron and the nucleus that's in the denominator in here, and then we've got also some unit vector. So this unit vector, sometimes written like this in future slides. So there's that unit vector. So this is classical physics. We're going to try to marry these two things together. So we now know that the force holding this electron in place as the electron kind of whizzes around the outside of the nucleus is provided by Coulomb's law, and the acceleration of that electron as it goes in this circular motion is described by classical mechanics. So we want to think about this centripetal acceleration, and that centripetal acceleration is given by again that's minus the velocity squared divided by the radius, and again multiplied by this unit vector that describes the position of the electron relative to the nucleus. So we're going to combine this, we're going to build this into F equals ma, right? So here's the force, mass times acceleration. So this term finds its way into this part of the equation, and the left-hand term is the force on that electron, that Coulomb's law force on the electron. We're going to find that some of these terms cancel, so the unit vector cancels, the minus cancels, and so we're going to end up with this ZE squared term over R squared. We've got an R that cancels in here, okay, and what we'll be left with is a ZE squared equals MV squared R, and then I'm writing at the bottom, so what? Why do we care about this? So ZE squared equals MV squared R. That's what we've just figured out. We've also got this idea of quantized angular momentum in here. So that quantized angular momentum is nh bar. And what we're going to do is substitute V equals nh bar over mr. Where does this come from? So we've got mbr equals nh bar. So V equals nh bar over mr, and we're going to substitute that into our expression ZE squared equals mv squared R in here, okay, and so we're substituting for this V squared, and these terms get pumped into this expression here. And when we rearrange now and solve for R, so basically the R comes over to the left hand side and the ZE squared comes over to the right hand side, what we end up with is the final expression on this page. Here we go. So we've got integers, we've got h bar, Planck's constant, divided by 2 pi. We've got the charge on the nucleus, we've got the fundamental charge, and we've also got the mass of the electron. So what can we write about R? We can basically say that R is restricted to certain orbits, and the smallest orbit, okay, that we have is when Z is equal to 1 down here and when N is equal to 1 over here, and we plug those values in. So we're going to cancel this because this ends up being 1 and the Z down here ends up being 1. So the smallest value for the radius is given as h bar squared over me squared. That is called the Bohr radius, a sub naught, and the number there is 0.0529 nanometers. And we're going to call that the first Bohr orbit. When we get to weeks 13 in the course, we're going to use this term a naught quite a lot. This is where it comes from. So lots of little bits and pieces here that are going to be useful later on. So now let's look at the energy of the atom. More bits and pieces here. So if we think about the total energy of an atom, here's our total energy here, is equal to kinetic energy and the potential energy. So total energy is equal to kinetic energy and potential energy. Here's our kinetic energy, all right, and we have determined already that kinetic energy from our expression 2 slides ago. After rearranging this, we can substitute for mv squared. So mv squared is equal to, take the r away here and throw it over onto the left hand side. Okay, and so that kinetic energy is equal to half ze squared over r. If we think about potential energy, we can also think about Hooke's law derivation. So we know the force here on that electron. So if we integrate the force with respect to the distance, this gives us our potential energy. I say this is similar to a Hooke's law derivation. I'm not sure we even need to go there to Hooke's law for now, but we're basically saying what's potential energy is it's force times distance. So we're integrating the force with respect to position in here. The potential energy defined as the energy required to take a particle from infinity to its position. And so when we substitute in the force, the expression for the force in here, that is we got a minus in here, and that minus with the minus outside here turns this into a plus, and then we can bring the ze outside of the integral, and so that the result of this integral ends up being minus ze squared over r. Okay, so interestingly, we've got a potential energy that's minus ze squared over r, and we've got a kinetic energy that's half ze squared over r. So what we're going to find is that when we put those things together, and this comes up again I think in chapter 8, but I'm giving you these little bits and pieces now. So we've got our total energy E is equal to the kinetic energy half ze squared over r minus the potential energy ze squared over r. So our total energy is equal to minus, it's actually the same as the kinetic energy, minus half ze squared over r. We know what our Bohr radius is, we know what our expression for r is, so we're going to plug this in here, and so ultimately we end up with a value now. So we've got E in terms of half minus half ze squared over r. We've plugged the r in, so what we end up with is this expression down here. And now, what's the link here? What's going on? If we look at this expression, we've got an energy term and we've got a 1 over n squared term. Where have we seen that before? It turns out that other than the n squared, we've got a bunch of constants. We've got the mass of the electron, we've got the charge on the nucleus, we've got the fundamental charge of the electron, and we've got h bar, Planck's constant over 2 pi. So what's the link here between E and n squared? These discrete energy levels appear because of the n squared in the denominator, right? N is an integer, so that's why we're getting these discrete energy levels. Remember, this all came from a proposition, a postulate that came from Bohr's assumptions. Okay, how do we tie this in with the experiment? We can link it to atomic spectra. And the bottom line here is we've got this collection of constants in here. We've got these n squared terms. Remember, we started this particular lecture by thinking about the difference between energy levels associated with the energy of the photon. And now we've got this collection of constants. And if we take this collection of constants, multiply them together, we get a number that is 109,737. Remarkably similar to the Rydberg constant that came up when we were talking about atomic line spectra. So this actually works out really well for hydrogen. What's the point of all this? The key here is that all these bits and pieces historically show us how we are moving closer to some key aspects in quantum mechanics. Angular momentum is quantized. There's something called the Bohr Radius. The Rydberg constant, that was an experimental constant, comes together as a collection of constants: pi, mass of the electron, fundamental charge, Planck's constant, speed of light. And it came from some assumptions and some postulates that were made. This is the nature of the beast with quantum mechanics. Lots of postulates, and it turns out that these postulates lead to a theory that works remarkably well. It doesn't explain what's going on, it tells us what's going on. So, in summary, Bohr's hypothesis is based on this quantization of angular momentum, and it fits the experimental data when we think about developing the Rydberg constant. Quantization explains nature. We're gonna find out that quantization is required for black body radiation. It's required for the photoelectric effect, and it's required for atomic line spectra. So this is just the beginning. What we're going to do in the next lecture is go back now more to mathematics. We're going to derive the mathematics. We're going to think about the rules of quantum mechanics. This last 3 lectures on PowerPoint basically sets us up to kind of recognize the context behind what's still to come in terms of the mathematics and chemistry of quantum mechanics. So thank you for listening today, and we will take all these ideas forward, and I'll see you in lecture 4. Thank you.